Okay, so from today we are going to record a video. Okay, I'll put the YouTube and the video, whichever you want. So homework is graded by Shandon, so you can pick during the middle break and so on. I'll put it here. Oh, but don't move here, so it will change the camera position. So okay, so couple questions in the WeChat. So one question: why is so special in the 2D conformal transformation? So one is the what was that? Yeah. So one is in 2D is the conformal transformation infinite dimensional, which coming from the fact that the Killing spinner, the conformal Killing vector is given by this way. So when d equal 2, so it's just so this can be written as so that the E mu is either homomorphic or anti-homomorphic in complex orient. So that's so now for the infinite dimensional, and furthermore, so the question he had is that what was that? So with the algebra, so Ln is given by so anyway, so when n is greater than 1 or n is less than let's see, -1, then it's not globally defined on S2. So this vector field is not globally well defined as 2, which means that the transformation E of z is z plus whatever E n minus z n plus 1. So this transformation cannot be realized by flow of vector field on S2. So, as I explained in the differential geometry course, the vector field, smooth vector field, will generate the one parameter family of the homomorphism, which is called flow. But unfortunately, so this transformation, if n is greater than 1 or n is less than -1, then this transformation cannot be defined as a flow of the vector field. So that here either 0 or infinity, this vector field is not well defined. On the other hand, for instance, SON is acts on Rn. So this is of course the homomorphism. For instance, this can be defined as the flow of vector field. This this is strange, but so this vector field will just generate the rotation as a flow. On the other hand, this cannot be. So the Monza transformation in 2D conformal transformation 2D cannot be defined as a flow of the conformal transformation. Okay, so that's and then somebody else asked about how to derive word Gaussianity. Is that the question? If not, just tell me. What was it? So since correlation function is so correlation function of phi whatever x1 prime phi xn prime is the okay, so the correlation function is invariant on the symmetry of the system, so that we use the fact that the so we use the fact that the phi prime of x is given by phi of x minus I omega a ga phi of x. And it just take a leading order of omega, and you get the order Gaussianity. So that's how you obtain the order Gaussianity. So just take the leading order omega. Does it answer the question to the student in the WeChat? If not, just tell me. Okay, nobody told me, so I'll ask a question. Is there any other questions? No, I mean, if you have a question, just tell me. I mean, I'm not sure if I understand the question correctly from students. Okay, if not, let me move on. So last time we talked about primary field in 2D. And now we apply the conformal symmetry to the volta Gaussianity in 2D. So last time we introduced the current for conformal symmetry, which is given by what was it? Yeah. So under the conformal whatever. This is a infinitesimal transformation. Then net current J of x is given by whatever T mu nu. That's and T mu nu is the energy momentum tensor. So this is I explained last time, and we just plug in this one into the net. Word Gaussianity. So then what we get is so domain these. This is the word Gaussianity for conformal symmetry. Okay, so so this is domain. So whatever two-dimensional, whatever C, we consider domain can be any D, and then later we will call which one? Counterclockwise C, maybe we will call the boundary we call C. Okay, in two-dimensional world, so we will define as energy momentum tensor in complex coordinate. So we just use the just do the coordinate transformation. 1/4 T0 minus 2I T10 times T11. I mean, this can be TZC. The whole part is just this is plus, and then this is just a. So as I mentioned in Gaussian theory, this energy momentum tensor should be traceless, so this should be 0. So if you write down the complex coordinate, everything is indeed just become diagonal, whatever. C bar, C bar. Yeah. And moreover, so we define as T of Z as minus 2 pi of TZZ, and T bar, Z bar is minus 2 pi T, so that's the we're going to use. So the reason why it only depends on holomorphic coordinate or anti-holomorphic coordinate is just a current conservation. So the equal to 0. So this means that the maybe I put the minus 2 pi, and Z bar and T equal to 0. So the reason why they are both either homomorphic or anti-homomorphic really come from this current conservation. Okay, so now we just apply this one into the here. So this the vortex Gaussian identity. So if you and then do the integral by parts. So if you do the integral by parts, so what you get is as follows: minus dc. So I just here this is indeed. So this is indeed equal to whatever. And then also plus partial z TCC of Z bar epsilon C of Z bar of X. So this is the becomes right hand side. Okay, so this is indeed can be written like this way. Of course, we define similarly to the stress energy tensor E whatever Z bar of C is equal to EZ of C is equal to EZ, and then epsilon C of Z bar is equal to epsilon C bar define. If you define like this way, and just perform, just of course d square z is equal to dz bar up to some factor. I will report that factor. It should be 0 to Jacobian. Is it to be? There must be Jacobian. I think 1/2. This is 1/2 maybe. 1/2. So therefore, yeah. And now, so we have a 2 pi here and 2 pi here. And then if you do the contour integral, then apply the Stokes theorem on this one, what you will get, or integral parts, whichever you call it. And then what you get is the as follows. Minus 1 to pi I dc E of z t of z x plus 1 over 2 pi I. Okay, C is this one. C is the boundary of this domain. Okay, so this is the conformal word Takashi identity. But to get a bit more meaningful statement, we focus on x is the correlation function of a primary field. So this is applicable for any local field. But now we focus on x is the primary field. So now x of W1, Wn is the product of primary field. So they are primary. And as I mentioned last time, primary field should transform under the conformal transformation is the I'm going to only focus on holomorphic part. So now, from now on, I'm just going to focus on holomorphic part. Holomorphic part. And the H is called conformal dimension. And now, so we look at the very omega is very as a before, just over there. So something like a z plus e of z. So infinitesimal transformation we will look at. Okay, so this is the so this infinitesimal transformation of the primary, it can be written as follows: minus h phi so this is the infinitesimal transformation for the conformal primary. Okay, so now and then we just write down this one as an integral form. So this one can be written as following: 1 over minus h minus h over 2 pi I I'm writing. Let's see. Oh yeah. Sorry. Okay. Okay. Let's see. What should I write down? Okay. Maybe I need to change a variable. Sorry. So since we want to put this one into over there, everything we want to write in w coordinate. So so what we have is the phi of w epsilon w of w can be written as 1/2 pi I dz epsilon t phi of w z minus w. So this is just complex analysis. We now have the following. So whatever point w, and then c is something like a contour around c. The z is around. And similarly, so if you use the so we are just looking at these term in w coordinate. So this is the you can write down in terms of the integral. Just use a Gaussian formula, Gaussian integral formula. In complex analysis, you get this. So now here, so we assume the in complex planes there is a whatever w1, w2, and w3, and wn up to wn. And we just take the contour as like this one. C inside of it. Okay, so you just pick all the point in the correlation function. Then, of course, as you learn in so this can be just boils down to the sum of all small contour around each primary. So at and they plug everything into there. What you get is the following. So just focusing on only the homomorphic part. So left hand side becomes sum of I 1/c minus wi. And of course, you can have this kind of stuff, minus 1/2 pi I, dz and c. And then right hand side, you have 1/2 pi I. C t of c of x. Of course, as I keep mentioning, just okay. So therefore, so just get rid of. So this can be applicable for any wi. So just get any wi, and z can be taken under any how to say the contour that contains all the primary. So therefore, this will give you the identity. Yeah, of course, I mean. So this will give you identity that the for primary field, what you get is just to get rid of this integral. And even if you have a regular term, it's okay. So up to regular term there. Okay. So even if you have a regular term, the contour integral does not see this regular term. So okay. question? Yes.
What is the HI?
HI is the component dimension of the primaries. Any other questions? Okay, so let's move on. So from here, so one can obtain the so-called OPE of energy momentum tensor, and the primary is indeed 1 over z minus w of square of h phi of w plus 1 over z minus w of. So where phi is the primary field, now I assume primary field, and this means that they just ignore regular term. So this is the called operator production expansion of T of C and the primary phi of W. So if it is not primary, so you have a singular term, more higher order singular term. So this is the OPE of the energy momentum tensor and primary field, and you have to use this relation entire throughout the whole courses. So you have to use this OPE relation. I mean, it's essential in 2D homomorphism. So we obtain very essential, important relation or whatever OPE of primary field. No. So this one you will use a lot throughout these courses. So for higher, so except the oh my goodness, what I'm writing. So this should be Z. So if it is the secondary field and not primary field, whatever, let's go phi tilde W. Then you have higher order term plus H scaling dimension Z minus W. So this part should be the same. But you have high order term for secondary field. So I should use this. For if phi tilde is secondary, not primary. Any question? Okay. So now we are going to move on the free boson, free fermion, and so on, and then Birasara algebra and so on. Okay, let's move on. So let's consider the boson two-point function. Bosonic field. So this is the two-point function of the bosonic field. We assume the phi is the bosonic field. Often in past integral formalism, we just introduce the so-called generating function of the correlation function, whatever. So here dimension can be anything. So this is generating function of the correlation function. So the reason why is that if you take the derivative of z with respect to this current J1, Jx1, delta Jx2, then what you get is that the and put the j equal to 0. Then what you get is z of 0 times phi of x1 and then phi of x2. So this is a correlation function. And that's how you obtain a correlation function out of the this generating function z of j. If you take a second derivative with respect to j, you can get, the number of times you apply this j derivative, you can bring down this phi of x into the inside the path integral, okay? So that you can obtain the correlation function. Okay, and most of people, in field theory, we will do the Gaussian integral, like say that s is equal to 1/2. So this is the kinetic term of the phi of x. Suppose it has a following form, or the action has a following form. So then, after manipulation, so suppose this is a quadratic term. So action takes the following form. Then this generating function here can be manipulated as follows: minus s plus ddx phi of x, j of x. Can be written as follows. It's just manipulation. It just link it to here, and then phi goes to 5 plus 5 naught. Then we'll get 1/2 ddx dy. It's just the ordinary one. A of x y. Phi of y. It's just, anyway, you have to do the same piece. Phi of x. I'm too lazy, so I'm not gonna write down everything. minus 1/2 of this one minus phi of x. Okay, alright. Let me do the. I'm a lazy person, so y not y, and then minus 1/2 phi naught. Okay, so that's what you get by just shifting phi goes to pi plus phi naught. Okay, phi naught. So this is very simple. The subscript x is just a variable x, and so on. You understand what it means. And then this term is just you get the just shifting of ddx. And the phi naught of x and j naught, jx, and then so this is the just shifting here. The reason why we did this transformation, we use the phi naught as the following. So if you choose dy of a xy, phi naught y is equal to jx. Okay. So we choose phi naught and satisfy the following form. Then we will get which means that the phi naught of x is dy. The inverse xy on j of y. So here we assume that this operator a. So usually if it is a free boson, this is Laplacian, and so on. Laplacian plus m squared and so on. So if a is the invertible, we assume a is invertible. Why not? It can be written like this way. Okay. Then plug that one into here, what you will see is that the this term, let's see, how do we call it? So z of j can be written as follows. So some number. So this is so phi of the phi exponential minus 1/2 ddx ddy phi x a x phi. And times, so this is a can be understood prefactor and times exponential exponential 1/2 ddx dy j of x inverse xy and j of y. Okay, so let's see how we get from here to there. So clearly, So this term, so if you this plug this one into here, you get this term. And the previous term should correspond to the dot one. And then we would like to see the rest of the terms should cancel each other. How do it go? Let's see. It's just the usual Gaussian integral you should do, but I already forgot how to do that. Yeah, so as you can easily see, so if you plug this one into here, that should cancel with this one. That's you can see, right? Do you understand? If you plug this one into here, this one cancels with second term. Do you agree? Okay. And the third term is just a Gaussian integral phi 0, and a should give you some number, so you can just drop it. So what's left is this one and that one. Okay. Or anyway, or anyway, phi is redefined as phi plus phi naught. Okay, phi plus phi naught. So therefore, you can combine them together. No, sorry, this is not the right way to think. Yeah, I think phi naught. So here it's a final path integral is field phi instead of phi naught. So the phi naught is already fixed. So therefore, this will give you just by Gaussian integral, you get just some number by Gaussian integral. So you can just drop it. And what's left is these two. So therefore, if you use this relation, then we just use the relation, the correlation function phi of x1 phi of x2 is indeed given by whatever some up to proportional factor second derivative of z delta j x1 delta j x2. If you do use this fact, and this can be written as some number A inverse of x1. So I'm very sloppy about the numerical. So it has 1 over z naught, and you have to be careful about this quotient. But I'm very careless about this quotient. But in any case, so this 2-point function can be written A inverse of xy if the action can be written as this quadratic term. Okay, so that's the conclusion. The action, if the action can be written in this quadratic term, so after this manipulation, we can just write down 2-point function of bosonic field can be written just inverse of this operator A. This is very standard in quantum field theory. It's very, very standard. And we will see this, we apply this to the free bosons. Any questions so far?
Why do you have ordering the actor nodes?
Just one moment. Let's wait this ball stops. So what did you say?
Why do you have time ordering the actor nodes?
Time ordering? I mean, correlation function, as I mentioned, if you define a correlation function, we assume automatically, we assume that the T1 is T2, Tn. So automatically. So the time ordering is always assumed. So here, we just have an explicit written down. Yeah, here, always time ordering a simple correlation function. Any other questions? So now, back into the 2 dimension. So here, this is a very general story. And now back into the 2 dimension. Suppose S is just free boson. I don't know. Somehow I use this chi phi for free bosons. So this can be written as follows, whatever. In the following way, so 1/2 d squared x. Oh, sorry. So then it should be d dx. Yeah. So the lecture note is correct, and somehow I made a mistake. So this is general d dimension, but now we are back to the 2 dimension. So this can be written as follows. So this is the, we assume this one. Let's, okay. So you just do the integral parts. Integral parts, you get Laplacian here. Okay. Laplacian here, and you just be careful about the normalization. So therefore, so we just want to have the inverse of this one. So this means that so from here, so A inverse, let's consider A inverse. So in the lecture note, I just write down kxy as A inverse xy, such that the minus 1/4 pi, and this is called green function. So already, so this is very standard in quantum field theory. So it's even Peskin, Schroeder, and so on, in just d equal to 4, you will get this one. And sometimes it's called Feynman propagator. Yeah. So, and then now, so as you can easily assume, so this function has to be translation invariant, so it only should depend on the difference between coordinate x and y. Okay. Moreover, it's a scalar function, so it should be written in terms of the absolute values. So suppose we introduce rho is the absolute value of this one, and just do the integration in the in terms of, yeah. So we will do the following conjugate. Yeah. So suppose we have, what we are going to do is you have x and y, the position x and y. Here we call it, this one is the rho. X minus y is equal to rho. Rho. And we will do the integration. So we integrate the all x and rho. Okay. So we just move around, integrate the all x, which means you have to also integrate the rho. So that will give you this relation. In the spherical coordinate, you will get the following. 1 is equal to 0 r. Let's see. So here, everything you should write down. Yeah, I think what I'm doing is following. Let me think a little bit. Yeah, I think. Okay. okay, let me do the following. So the delta 2 x minus y, d phi and the d rho. Yeah, and rho. So everything, so this is only depends on rho in the rho equal to 0. So this is equal to 1 up to some factor. Maybe I should, so to get the right result, I always need to get the right result. Okay, this one I didn't derive, so okay, so you guys should derive by yourself. You will get, if you do the appropriate coordinate transformation, I already forgot how to derive this one. The rho minus 1 over rho k prime of rho. So this is Laplacian, here, Laplacian. In the polar coordinate. And then here you will get 1/2 minus r k prime of r if you integrate 0 to r, and here also we assume this is equal to 1, delta function over this polar coordinate. Okay, so to satisfy this condition, of course, what we need is k of r is equal to 1 of log of r square, right? 2 times, yeah, 2 times. Maybe with minus sign, yeah, minus sign. So the solution of this equation is clearly log minus 2 times log of r. Okay, or r square, whichever you call it. Okay, so here, so we just solve this the integral. Here, my derivation is very sloppy. I think sloppy, but I mean you understand what it means. So from left hand side you get 1, and you just write down everything Laplacian in the polar coordinate and just do the integration. And you obtain the k of r, which is proportional log r. So therefore, the 2-point function of the 2-point function of this free boson in 2 dimensions can be written as follows. So now, from now on, so we will study this free boson example more in detail. So we know the compound primary of phi of w is already so. I think is it too early to mention give you this counter? Okay, I think it's a bit too early to give this answer. Okay, maybe it's better not to. So now, so we will study this free boson example more in detail. To do the, we will use so-called, for instance, in free boson, what is the primary field? The question is, what is the primary field, and how do you construct the primary field? So, and so on. So to do that, we will introduce so-called Weak Theorem, and from now on, so we just focus on the free boson and determine the correlation functions of free boson and all the spectrum eventually. How to obtain the partition function of free boson. And so that's we are going to see from now on. Okay, so any questions so far? Okay, so to understand the OPE, so we would like to understand the OPE in free bosons, even inside a primary field or secondary field. So we need to use so-called Weak Theorem. And if you take the quantum field theory course, it's very, very standard. Okay, standard. So here we just phi of x. So again, we go back to the standard quantum field theory. The phi of x is now the operator in quantum field theory. So we just use the phi plus of x plus phi minus of x. So this is the annihilation operator. And this is the creation operator. So we just, I mean, essentially you do the Fourier analysis, whatever, I mean, integral or summation, whichever you call it, depends on how to say, you put the boundary condition or not. And you do the Fourier transformation, essentially ikx and iak and ak dagger e to the minus ikx and so on. So this is essentially what you do. So the k is the either summation or integration. And in quantum field theory, so this ak and ak dagger is become creation annihilation operator. The Shao already. How many of you guys is taking QFT now? Almost half. Okay. Did he explain already this one? Not yet. This free
last course.
Okay. Okay, so that he already explained about this, how you decompose the creation annihilation operator. Yeah. So we treat this phi of x as some operator, and then so we decompose the field in terms of creation part and annihilation part. And now we introduce so-called normal ordering. So normal ordering is phi of x1. I mean, it's very simple. You just put all the creation operator to the right and the annihilation operator to the left. So this is just a phi of x1. I mean, it's boring. I mean, if you know, it's a boring definition, but eventually you have to be careful. I mean, about definition. So this part is very simple, but the cross term is non-trivial. And always put the annihilation operator to the left and the creation operator to the right. And then time ordering, if you consider time ordering, where the x1, so then this can be understood as the following. I mean, it's super boring. I mean, so I'm not going to head down. So I'm not going to write down, but the difference can be understood as the combination. The difference between time ordering and normal ordering can be understood as the commutation relation of the annihilation part of creation part of x and annihilation part of x2. So this can be just do the direct computation you can obtain. So therefore, yeah. So therefore, so this can be understood. So this part. So you have to apply this the computation relation creation annihilation operator, and at the end of the day you get some just function. No longer this becomes operator, and it becomes function. And indeed you can just consider as this is 2-point function. Oh my goodness, I told you completely wrong. Sorry. Why you guys do not point me out? Yeah, the opposite. So that's why I got confused in the middle. Huh? Yeah, the other one. Sorry. I'm very sorry. You guys should. And the creation. You guys should. Okay, so normal ordering. Sorry. Sorry. It's recorded, unfortunately. So put everything, the annihilation operator to the right, and then put the creation operator to the left. So therefore, if you apply, if you apply the vacuum excitation value t of phi of x, you guys should tell me. In here, I mean, so this one is everything, all the annihilation operator to the right, so that everything annihilates vacuum. Okay. So this doesn't if you just sandwich by vacuum, this will give you 0. Okay. This will give you 0. So therefore, if you can sandwich the vacuum, this will give you 0, but the constant term or some function is indeed the creation function, become creation function. Okay. Do you understand? So now, to compute OP and so on, so we just introduce the so-called weak contraction. It's very simple. So we just introduce the following notation: phi of 1 of x1 and phi 2 of x2, and just contract, then it's defined as the 2-point correlation function. 2-point function phi 2 of x2. So this is just functional in terms of x1 and x2. So and then Weak Theorem states that the time ordering operator of this one I'm already supplies the x1 and x2 and so on can be understood as the normal ordering let's. I don't want to do the 4-point function. Let's do the 3-point function instead. I'm too lazy. I don't want to write everything. Maybe do the cyclic way. So this. So the Weak Theorem mentioned that this time ordering of this operator can be understood as the normal ordering, the product, and then possible way of contracting. Possible way of contracting. So this is exactly what we saw in 2-point function, and the 3-point function is almost same. 3-point function almost same. 4-point function is written in the lecture note. And then moreover, so you can just consider the following time ordering. So it's a bit more complicated time ordering. I suppressed in terms of variable. Maybe I should write that? Maybe here it's in the same place, and then y and y. And then we will do the almost same exercise, but the following way. Here, of course, I just assume x1 and x2 and x3. I just suppress all variable here. And all possible construction. For instance, like this way. Sorry, I don't need this one. Sorry, I don't need this one. Okay, so I'm too lazy, so let's do the color choke. Color choke instead of writing everything down. So white choke is improved, but color choke is not improved yet. So here, only you just take the contraction with different sector. Okay. So here, another way to contract is this one, and furthermore you have this guy, and also you have this guy. So this is a statement of Weak Theorem. And then, so this is single piece, and plus phi 1, phi 2, phi 3, and phi 4. And then you have the and then also so the other way to contract. Okay. So now for thin contraction, you have 1, 2, 3, 4 term. I just suppressed the 4 term into the single term by with coloring, and you have 2 simultaneous contraction. That will give you just function. This will give you the normal ordering times some function. Okay, that's how you obtain the time ordering of these 2 normal order operator in terms of the normal ordering by weak contraction. So so this normal ordering. So if is that you just put all the annihilation operator right and the creation operator left, so that if you sandwich by vacuum, you will get 0. That's how you obtain. That's why this normal ordering is important. So it's insensitive about the vacuum excitation value. And what's left is important. Okay, so this is the statement of Weak Theorem. Okay, so maybe this is Weak Theorem. This is Weak Theorem. And now we are going to apply this Weak Theorem in terms of the in the correlation function. No, in the free boson. Okay, free boson, I already erased the action, but the S is equal to 1/8 pi d square x. Okay. And we already know 2-point function for correlation function. Of course, the equation motion is the Laplacian equal to 0. And in terms of complex coordinate, you get and then, so it's easy exercise to derive that stress energy tensor T min nu is indeed, everybody should do this exercise for phi mu. So A min 1/2 A min nu. So this is the stress energy tensor. And then, if you write down in terms of the homomorphic coordinate, it's very straightforward to do the exercise. Okay. So this is classical statement. This is a classical statement. And in order for the vacuum excitation value should vanish, so in quantum mechanically, you should put the normal ordering. You should put the normal ordering. So this is a quantum statement. So so the 1-point function of the stress energy tensor should be here. Any questions so far? So it's easy to see, right? So in holomorphic coordinate, A to ZZ is equal to 0, as you know. So then you only have this one. Maybe I should. I don't need. Sorry, I think minus 2 pi. Sorry. Yeah, this is correct statement. Okay. So the one consequence of this one so phi should be equal to holomorphic, and the phi bar of phi should be anti-holomorphic. So as you can see, so if you apply phi bar again, this should be 0. Okay. If you apply phi bar, you should get 0. So therefore, no phi bar, so del bar. Del bar. If you apply del bar to this operator, you get 0. So therefore, del phi should be holomorphic. Okay, and also if you apply del to the del bar phi, you get 0. So therefore, del bar phi should be equal to anti-homomorphic. Okay. So therefore, so if you multiply the del phi and del phi, it should be holomorphic quantity. So this pitch is consistent with what we have observed last time. Okay. Just like 1 hour ago. And also, okay, so that's the case. And we already knew that the two-point function of the operator, two-point function of this one is, so we know this is equal to minus log of c minus w squared, which is equal to the following. Minus log, you just decompose anti-homomorphic and homomorphic part. Anti-homomorphic part. Okay. Therefore, it's straightforward to obtain two-point function of del. I mean, okay. Let's focus only on. Okay. So as I mentioned here, so since del phi only is holomorphic object, so this can be understood as just applying del z and del w into to this log. And what you get is 1 over so therefore OPE of can be understood as okay, so that's how you obtain. Any questions so far? Okay, let's take a break, and then after the break, I will do lots of OP computation from now on. Lots of OPE, and also hopefully I will get to the point of universal algebra. Okay, let's take 10 minutes break. And just if you have a question, please tell me. Oh yeah, so homework is graded. So if you submit in person, you should pick the graded homework. Yes.
You state this field is holomorphic field, right?
Yeah.
But it's based on classical equation of motion.
Yes.
But why the quantum field should obey the axial classical equation of motion?
good point. Let's see. Good point. Let me think. Oh, yeah, I will. Even operator, even operator-wise, it should be the case. Let's see. How can I see that? I mean, it's a good question, but I mean, even in quantum mechanical, this should be the case because, I mean, to obtain these, for instance, Ward-Takahashi identity, I mean, even like a, how to say? So the classical equation is the current conservation is this. So of course, this is classical, but quantum mechanically, this will become something like how did it become? Even quantum mechanically, so this becomes something like a x is equal to whatever minus I sum over I equal to n delta z minus zi and x, essentially whatever. So this is the Ward-Takahashi I introduced. But if this is really depends on z bar, if really z bar, you clearly this downward should act on this z bar. So therefore, you won't get the homomorphic quantity in the right, even correlation function wise. So it should depend on only for homomorphic coordinate. Yeah, even quantum mechanical. Yeah. To get the Warta-Gaussian identity. Yeah. Similarly, even here, phi of z is indeed the current. So this can be understood as the homomorphic current of phi goes to phi plus some constant. So this is invariant under this action is invariant under this transformation. And the Nessa current of this one is indeed this one. So therefore, partial whatever. I mean, z bar and jz bar is equal to jz. This one. It should be equal to 0. This is how to say Nether theorem. But if you use the Warta-Gaussian identity, you really need also quantum mechanically this the operator should only depend on homomorphic. Otherwise, this anti-homomorphic derivative really hits on the z bar, which will give you non-trivial to the right hand side. So the Warta-Gaussian doesn't hold. So if you have done homework, please hand in to me today. TA is not around, so if you want to hand in person instead of online submission, just hand in now.
That's a question about homework.
Yeah.
Because when I try to reproduce the current for this term, if I use the equation of motion with this current delta I phi, this term will become, and after I integrate the part, this term will cancel this. And the final result will this one term, last term. But if I use the description or lecture or the terms with W can be cancelled.
What?
Because all the yellow book says all the terms with W can be arranged.
Okay.
So if I use that, I can reduce the curve. If I use the equation of motion this time I cancel this time. That is the maybe the motion is not
Why is the Gaussian motion this term is not present?
because usually equation of motion this time becomes partial. This. And if I read the card, I get minus this as a mu of liter time WA. this term equals to this, and we
Okay, but how did you get this one?
on this time, all the terms with WH are vanished.
Why?
And this side. Result on this variable.
이게 3mm. 아, 내 생각이.
Oh, yes. Understand. Reaction can come with no reaction. Yeah, nice. We go on with first reaction.
Okay. Okay, so if it is invariant under the rigid transformation, so the action is invariant. Okay, that I agree. That I agree.
Yes, by using this description, I can reproduce this curve.
Okay. But is it different from equation motion?
Yes. If I use equation motion with two times constant, and we don't have the last term.
How do you get the last term? My question is.
Because this one is a term with WA constants, and the pressure mu act on the later one,
Okay.
and let the WA outside, and this also constant.
Okay.
We will let this pressure mu only A with this. And this one is the last term.
Okay.
Using equations motion these two times concepts. So I don't know what happened. Maybe boundary terms not vanished. The equation motion not true anymore.
I'm sorry?
I mean, maybe the boundary of the variation, the delta, maybe delta phi at the boundary is not there. this equation of motion is not true.
Isn't that the rigid transformation? Also enforce equation motion? It looks to me if you assume omega A is rigid, you just get the equation motion. All term vanish, right? Or omega proportional this term all vanish. But what you get is essentially so this is constant. Integral of parts. This is constant. What you get is delta L. Essentially, the equation motion. Yeah, so essentially, if omega is rigid, so you just saw this. Essentially, you use this equation motion. And then they vanish. So to derive this, and essentially you use the equation motion. No, I mean if you assume omega A is constant, so from here you get the equation motion. So essentially you use the equation motion to derive this. Okay, let's talk about that. So let's start. Okay. That's fair. So where are we? Okay, so we derive this this OPE of two operator to find So now, so we would like to look at the OPE of this guy. And this is equal to 1/2 minus 1/2. As I derive, the stress energy tensor is and then we apply the Weak Theorem to see the OPE, so we just have this one. And now, so we know that the phi of W is minus log z minus W. We plug that one into here, and then we will get is indeed z minus W square of z. So remember, so this is z derivative, this is W derivative. Z and W derivative. And then you just apply z and W derivative, you get the 1 over z minus W square, and just cancel 1 minus 1/2. And then do the Taylor expansion. Do the Taylor expansion, this is equal to, maybe already this one, this is equal to, indeed, okay. So that's the OPE between energy momentum tensor and the derivative of phi. So therefore, from here, so what is so it's the primary of conformal dimension. What? Conformal dimension what? So what Takahashi identity tell you? Are you guys awake? So what Takahashi identity tells us that the primary should obey this OP rule with energy momentum tensor. So what is the conformal dimension of del phi? Huh? Yeah, 1. So it should be 1. Which is quite natural because I mean, so we start with this action. And of course, scalar dimension of del is, of course, scalar dimension del is equal to 1. And the d2x is scalar dimension minus 2. Therefore, what is the scalar dimension of phi?
1.
No. Huh? Yeah, it should be 0. So here this is minus 2 plus 1, from derivative plus 1 derivative, there is no place, it's balanced already. It's scalar dimension 0 if you add them up. Phi should be 0. This is the reason why the 2-point function should be log. Okay, should be log. And if you apply the derivative phi, derivative del to the phi, so this is scalar dimension del is 1. Therefore, del phi scaling ratio should be 1. And it's primary, so it becomes compound dimension. And the compound dimension is equal to 1. Okay, so that's the case. So that's the case, and then where are we? Where are we? Hey, you can do the same exercise for TTOPE. So as I mentioned last time, so if you have 2-point function of the whatever primary of t, phi 2 of cw, it should be equal to constant 1, 2, t minus w, and 2h. And in this case, phi 1, phi 2, if you start with this free bosons, so the compound dimension of phi, Kali phi is 0. So what is 0? T minus w to 0. You get log. Do you understand? So the reason why del phi of z, del phi of w is equal to 1 over z minus w. So we already see, right? This one. Sorry, h. So here, this is one example. The 2-point function of primary is really obey this rule. Okay, we witnessed already the 2-point function of the primary obey this so this one we derived by just using the SA2C, PSA2C for quasi-primary. So you understand? You understand, right? So the quasi-primary so he's inside the primary. Okay. So therefore, if the am I correct? Yeah. So yeah, if the so by using only the quasi, so the SA2C condition, we derive this one. And now, so we see the one example by using free boson that obey this rule. So now, so h, the compound dimension of h is equal to 1 for del phi. And now, so here, so we are going to compute t of z, t of w. In the following way, is here. So here. Okay, I think I should do the really calculation. I'm very okay. -1/2. So you guys, so from now on, you guys need to do lots of P calculation. But I will give one example from now. So this should be times -1/2. Okay, then let's do the following +1/4. And then just apply Weak Theorem many times. So one is this one. Will give you the following 1/4. I don't want to make a mistake. Let's see. So I don't want to make a mistake. Minus log. So this is the phi z and the phi w of E. And we just apply z derivative and w derivative, and then what we'll get 1 over z, and then I think plus 1/2 z minus w square. Do you agree? Just correct me if I'm wrong. From this orange, and then we should do the following. The same thing for. So this one, yeah, you should get the same thing. So everything should be the same, right? And also here and here. So you should get everything the same. Yeah, you should get everything the same, so then times 4. Okay. And another thing we should do is the following: the weak contraction with the this one, and in addition to this one. Then what we will get is indeed. Oh, sorry. So this is what we get. What did you say?
It seems there is no 1/2 since it should be minus 1 over the minus.
Oh, you're right. Thank you very much. So if you apply the let's say axon z, you get the minus 1 z minus w, and if you apply w, and what we'll get z minus w square, and then we'll get the minus sign plus. It should be. Should I get minus sign? Yeah, I should get minus sign. Okay. Good. So I have to be careful. Yeah, I think I'm minus sign. Okay. And if you apply twice of this one, you get the same piece, z minus w to the square minus 1 to the square, right? Okay. And then, so this contraction and also the other contraction. So the other contraction should appear, so therefore then times 2. Okay, so this is OP. Okay, do you understand? And then what we will get is indeed 1 over 2 z minus w square. Okay, and then the quarter should cancel minus, so z minus w square, and now so we just do the Taylor expansion. And then we will do the Taylor expansion, so we'll get the divided by z minus w, and I should have 1/2. Do you agree? Yeah. Do you agree? So this derivative can act on both, okay? Can act on both. That cancel with this both, and 2 cancel with this one to get this Taylor expansion for this piece. Okay. So I just do the Taylor expansion z in terms of w. Okay. So I just write down everything in w coordinate. So here everything in except in terms of w. Okay. So therefore, so this is equal to this is equal to Okay, so in general CFT, if the CFT is chiral, non-chiral, CFT, non-chiral means the holomorphic and di-holomorphic sector is the so this the non-chiral is the holomorphic and di-holomorphic sector is equivalent. It's the same CFT. Non-chiral CFT in general TTLP the following is the following. Okay, so that's the. So this is the usual form for non-chiral CFT, where C is called central charge. Okay. It's called central charge. So this is for general CFT, and in the case of free boson, what is the central charge? So C is equal to 1. And this central charge is the most important quantity in 2D CFT. So given a 2D CFT, the first goal is to obtain, given a CFT, first goal is to obtain this central charge C. So it contains the most important information. As we will see in the subsequent lecture, we will see like a Zamago's C theorem, this C really, how to say, measure the degrees of freedom the CFT has. In the case of the, free bosons, the central charge is equal to 1. And as you can easily see, now from here, T, energy moment tensor T is not the primary field. The primary field should obey TT of stretch energy tensor with this rule. Needs to obey this rule. On the other hand, when you take the energy momentum tensor itself, you will get the higher order term. Okay? Therefore, the energy momentum tensor itself is not the primary field. Okay? Okay, so any questions so far?
Are there any examples of quasi-primary fields but is not primary?
Quasi-primary field, but not primary. Quasi-primary field. There must be. There must be. Quasi-primary field, not on the top of my head. Quasi-primary field is not the primary field. I don't know, to be honest, at the moment. So nowadays, technology improved. I just search in Google. But unfortunately, that doesn't give me the result. Okay, I cannot give you an example at this moment. I'll search later and let you know. Any other questions? Yes.
So what's the difference between the local and global in the quasi and primary?
Local and global. What do you mean? No, I don't understand your question.
In the definition of quasi primary field,
Yeah.
we need a global transformation.
So we just have the z equals to z plus b cz plus d. A, B, C, D. Yes, so this is the definition.
So what's the difference between the global and the local? The primary requires to in the local condition.
The primary is the all holomorphic transformation.
Oh,
So this is the part of the holomorphic transformation.
Oh, this is just a part.
Yeah.
And
This is only just homomorphic, just particular holomorphic function. Right?
So this can be only used to the quasi-primary.
To define the quasi-primary, we only use this transformation, but there are infinite many other holomorphic transformation, which is conformal. Any conformal transformation to define the primary field.
But in the lecture notes, you said it is a field who transform under any local conformal transformation. I think this
Any conformal transformation.
Yes.
Then it's misleading. Okay, I will erase this phrase. Any other questions? Did I say so? Okay. I agree. Any local conformal transform. Okay, so that's misleading. Okay. So I will erase any conformal transformation. Any other questions? Okay, so now, we derive for TTLP for free bosons, and then we'll see the consequence of TTLP. That will lead you to the Russell algebra. I'm not sure if I can beat that part. So before then, let's so this is not primary field. So let's look at how this energy momentum behave under the conformal transformation. So the Ward-Takahashi identity tell us that this W, let's W, is minus 2 pi I. Epsilon z, dz, and dw. Okay, so this is what Ward-Takahashi tell us, and this is equal to 1. Let's see. And we just plug this one into here. C of z. C over 2, z minus w to the fourth, t of d w, z minus w. and do the just contour integral or contour with respect to z. So now we are doing that again, the w here, and do the contour integral like this. And then what you get is equal to 1 over c w cube e w minus 2t w e w e. So that's what you get. It's very difficult to read off the finite transformation from here, and I just give you a result. This is infinitesimal transformation. The finite transformation indeed is given by like this one. So if you have only this term, it's just the t is primary, but we know t is not primary. The cost will show up in the next term, c over 12, and this is famously called Schwarz-Term derivative. This is exercise, so the homework is to derive from here to here. In principle, one can derive this finite transformation. And this is called Schwarz-Term derivative. So, whose infinitesimal version becomes like this way. But that can be, I mean, so derivation, that's easy exercise. Derivation is for homework. Okay. Okay, now we are going to talk about the bit about radial quantization. Okay, I think we can go to the Birasol algebra today. Birasol algebra, and then. So now, so we will do the so-called radial quantization on state operator correspondence from now. So now we will talk about the radial quantization to obtain the Birasol algebra moreover state operator correspondence. So here we just use the how to say? You just consider R2. And then the spatial redirection and time direction, maybe t or x and so on. And then we just consider time ordering in correlation function. But now we are going to do a bit more different way of looking at in the theory. So instead of looking at R2, so we'll put the theory on a cylinder. put it on a cylinder, and now so we consider this is the spatial direction x, and here is time direction t. Seems like my election was the other one. Yeah, I think I should use this direction. So put the cylinder, and then now do this following the we know that and also in the last time, so we just consider so L0 plus L0 bar is give you the okay, I think I shouldn't use okay, so here we just introduce the complex coordinate xc is equal to t plus ix, and now use a component transformation. So z is equal to e to the 2 pi c over L. Then what you get is c such that the c star, which is equal to c mod origin. Is a map, so the homomorphism to the so if you do the this is surely is a homomorphic function, and then so the circle, each spatial direction can be mapped to the circle here. So this is the origin 0, and the spatial circle is mapped to the circle around the origin. So that's how this component transformation, and this time direction is really the this radial direction. Is radial direction. So therefore, if you go to the future infinity, you get the really infinity on the complex plane. On the other hand, if you go to the future past, the past infinity, you gradually approach to the origin. That's the component transformation you get. And then last time, so we introduced a weak algebra, and we know that this one will generate the, I forgot, this one, right? And then L0 minus L0 bar is equal to theta. Okay. So this is indeed it becomes a really derivative with respect to t, and this derivative with respect to x in this coordinate, okay? In this coordinate, t and x coordinate. So rotation t, and this is r. Oh, sorry, the other one, sorry. If you did. Therefore, as you know, so in this the cylinder, so the t direction is really Hamiltonian is L0 plus L0 bar, and then this rotation is really spatial translation. So therefore, it becomes p in this cylindrical coordinate. So it's just this rotation is really the spatial translation in this cylinder. So H and P really corresponds to the L0 and L0 written by L0 linear combination L and bar, and somehow you need some sign here for the purpose of lecture. So, and then so the time ordering here, if you put on a cylinder, time ordering here becomes really radial ordering now. Okay. So therefore, so we can introduce so-called radial ordering. So radial ordering of phi of whatever W, I will call Z, whatever, and Z1 and Z2 is given by phi Z1 by Z2 if the radius is greater than, and then phi 2 Z2 phi 1 Z1 and okay, so this is radial ordering. And from now on, we will consider mainly radial ordering. So therefore, if you consider the radial ordering, so the consequence of this radial ordering is as follows. So if you consider the contour integral, for instance, whatever C-plane, and whatever the origin, and there is W here, and they just consider the Z integral around here, which is given by A of Z, B of W. Here now we assume the radial ordering here. Okay. So then radial ordering. So implicitly, so this is here, mostly radial assumed here. So then we just do the following integral. Let's see, and then. Maybe I should order in the same way and then use radial ordering, maybe. Whatever, whichever. Is equal to blue. Minus, maybe I should use. Okay. So one can introduce, if you use a radial ordering, so this contour integral can be written as the, of course, on W, Z is greater than W. On the other hand, for a red circle, W is greater than Z. So, okay. So you just introduce the radial ordering so that the you can just consider how you integrate this contour integral. So now the consequence is that in compound field theory, there is this very important fact which is called the state operator correspondence. So introducing this compound map is this compound map is the so-called give you the state operator correspondence. So in quantum mechanics, Hamilton formalism. So if you have the cylinder, at the Hilbert space, so this is this. So the state live in this world. In spatial direction, some state is given by whatever. Some state, whatever state phi sits in Hilbert space. In Hamiltonian formalism, you just how to say? Given a states, and the Hamiltonian will give you unitary transformation on the under the time translation or time development. That's how you see that. And in this conformal transformation, the state is defined on this circle in radial quantization. State defined on circle, so this will define the state in circle. But as you know, the scaling transformation is indeed in the conformal transformation. So we know that the scaling transformation is conformal transformation. So therefore, you can map this state and just shrink to the origin. Okay, you can shrink to the origin. At the end of the day, by conformal transformation, all the states are equivalent because the series is conformal. At the end of the day, so if you do the scaling transform to the origin, at the end of the day, you get the state which shrinks to the point, and you get the operator corresponding to phi of 0. Okay. So therefore, in conformal transformation, state defined on a circle in a radial quantization is equivalent by conformal transformation just squeezing this circle into the origin. So that's called a state operator correspondence. This is only happen in conformal field theory. And in general quantum field theory, so you cannot squeeze this state into the origin because usually this scaling transformation is not the symmetry of the theory. It's not the theory, it's a symmetry. It's symmetry of the theory. So therefore, so the phi corresponds to operator phi of 0. So this is a very simple statement, a very powerful statement. Unless you don't have this state operator correspondence, due to this state operator correspondence, one can compute many, count lots of states in conformal field theory. And so this is the essential point of conformal field theory. And in particular, so we just use the following things. So the phi of in state can be understood as a limb of phi of t and z bar acts on vacuum. Acts on vacuum. In particular, so in CFT or in physics, we usually impose so unitarity condition or like a positive definite condition on the Hilbert space. Okay, so we just, for instance, so we just impose whatever phi 1, phi 2. So in Hilbert space, we just have an inner product like this way. Hilbert space inner product. We want to introduce inner product in Hilbert space. Actually, Hilbert space, by definition, you should have some inner product. And it should be positive definite. It should be inner product and the positive definite. So this will give you the so-called Hermitian condition, the defined Hermitian condition, so that the phi, So we have the bra state, whatever. If you have bra state, we want to define a ket state. So that is indeed given by the dagger condition. The conjugate, Hermitian conjugate condition, which are given by okay, so there's a type here. So here we just state, just look at the sphere at a point, at the nozzle point, and phi of z equals to 0, and phi equals to z equals to infinity. Okay, by just the dagger is just mapped by let's see. By the component transformation in such a way that the everything well defined. So let's check the following thing. Let's see. Let's see. If it is primary, so phi of z, 1 over z, should be what? Is it the case? Is it the case? Do you agree with me? Are you guys awake? Just tell me if it is correct or not. If it is phi is primary, is it correct? It's correct, right? So just so therefore, if we plug that in here, to z to h and z to h. So therefore, you just impose z equals 0 at the if you, I mean here from z equals 0 to z equals to infinity, you just go to z equals to 1 over z, right? Maybe minus 1 over z. That's more appropriate. Whichever, 1 over z is also okay. It's a homomorphic function. Okay. So then so z equals to 1 over z, you can go to the infinity, okay? And it just multiply if it is phi is primary, so this dagger is just the same as the condition for origin. Going to origin. So that they counter to each other. That's how you define this dagger operation. Okay. What is 3.39? So any questions so far? Okay, and another way to look at this 2h is as follows. Another way to look at the following, so the that is, if you consider this 2-point function, the inner product, so this can be understood as z and w goes to 0, where the and if you go to cylindrical component, by component transformation, this can be understood up to h and then phi c, and lots of mistaking here, typo. Okay, so that's how you obtain by component transformation. And since, so we know this is proportional to 1 over h, h bar to h. 2-point function is 1 over c to h bar. That should cancel with this one. Okay, and so that the c goes to infinity limit should be well defined. Essentially, it's so this c12 I introduced for 2-point correlation function reappear as the inner product of phi in and phi out. Okay, unfortunately, I don't have a time to introduce the Birasar algebra, but I think it's a good exercise to do. Yeah. Okay, I think I just give you one comment about Birasar algebra. So we do the following expansion: T of z, sum of Ln, m is integer, and then z minus n minus 2. So this minus 2 is really scaling dimension of the stress energy tensor. And we know, so to get the computation relation, so now t is considered an operator. So if you consider if you want to get the operator, so therefore L is or L is also operator. And to get this computation relation of this operator, so we need to consider so you need to do the following the counter integral in radial quantization. In radial quantization, and the consequence is called a Birasar algebra, which is going to be a homework this week. Okay, so you have to perform this the counter integral in radial quantization. Okay, so we will see in 1 week. And I'm too busy. I haven't posted homework yet, but hopefully till this evening I will post homework. Okay. Any question? So I haven't answered the question. Let me think a bit more. I have an answer to the top of my head.
I think I understand your calculation, but I just don't understand why now it cancels the total term.
What?
I just don't understand why not to the use the equation of motion, integrate the part, and cancel the total terms.
Cancel what?
Because in your calculation, you have using these terms, two terms, and you left one term. You left this. You keep this term.
Yeah.
But you integrate the partial with this term and cancel with the first term.
I understand what you mean.
But the two terms can cancel two terms.
I understand what you mean.
基本上都有，就是你看着前面一个事情。
So probably just a choice. Make the current have the relation with respect to capital F. Just a choice of us.
No, it's not the choice. Oh. Okay. So I already explained here. So the action is invariant. Omega A is constant. Well, here we treat omega A as the just ordinary some function. Okay, so the omega A. So if omega A is okay, I understand. So if omega is constant, it's a symmetry. So the action is invariant. But if omega A is some function, it's no longer the case. The action is not invariant anymore. So so that the distance will show up. You don't need to use the equation motion. To derive this current. So we don't impose the equation motion. Sure. So here it's more like we want to have the necessary current is conserved instead of the equation motion. So we don't impose the equation motion. We just impose the action symmetry under the invariant under symmetry. Oh, I think I should stop.
I check the game.